Welcome to Weld.com. Been teaching for a long time. And in that time, I've noticed a lot of people that come to us for boot camps, for procedure work, make some pretty common mistakes. Today, we want to do a simple video on how to get into TIG welding, what these mistakes are, how to avoid them, how to correct them. So I'm going to put a TIG torch together, run some beads, make some mistakes, show you how to correct all that. Okay, quite simply, this is our TIG torch, and I'm going to put it all together and explain a few things. This is a 17 air-cooled torch, 17 series, and it says FV on it. F means that it'll flex. I don't care about that right now. I'm just telling you the ability of this, what this means. F means flex, V means valve. We have this torch on this machine because we run multiple processes and procedures. We're doing all kinds of stuff. It just happened to be on here today. Just don't worry about this. I'm just going to leave it open all the time. So, first things first. We have 3/32 or 2.4 millimeter tungsten E3. I need to have a collet and a collet body that are sized to the tungsten. The collet has a slit down through here, and it works like this. This will slip through here easily until I put a little pressure on it, okay? And now it's kind of stuck in there. So how this all works is when I get everything in the torch, the back cap pushes on the back shoulder of this, forcing it into a standard collet body. So by this being pushed on the back side of this, it's now, I can't put enough pressure on there with my fingernail, but I'll show you in a minute. This is what holds the tungsten in place. So the way all this goes together, these are copper alloyed fine threads. They're soft. You can be careful with them. Same thing inside the torch. Be careful of cross threading, and there's no reason to over tighten anything. So I'm going to thread this up here until I feel it bump or shoulder up in there. Now it's seated, and I didn't over tighten it. I don't need to grab needle nose or any kind of pliers and crank down on this thing. Okay? Next thing is the back cap. Again, fine threads, soft threads. And there is a surface back here that lines up with the back of the collet. So I'm going to insert this. I'll also notice that there's an O-ring on here, and that keeps your gas going through the torch, not out the back side. And I'm going to thread this on until I feel it touch or bump. Okay, I'm going to check this again. And then we can insert the tungsten up inside the collet, through the collet body. This is loose, and I'm going to turn this until I feel it touch or bump, and this is now snug. And that's all it really needs to, that's all it ever really needs to happen. Here's what I notice as far as problems. I have students that come to me and they say, well, my tungsten is loose and I can't get it to stay in the collet. 99% of the time I already know what's happened. What's happened was, and I'm going to back this off a little bit, and I'm going to loosen this. And now I'm going to thread this down. When somebody was messing with a torch or putting it together, they probably had this threaded down all the way. Big mistake. They had this down snug, and then they threaded the collet and collet body up there. Guess what? This is still loose. You know, and then the first natural reaction is, well, I'm going to crank down on this. I know, I'll tighten that thing up. I'll get her to stay. It doesn't happen that way, okay? Or they might take the cup and thread it on harder up into this insulator. You can tighten all this stuff and it just does. This is still loose, you know, it'll still move. So the key things are, back this off. You don't need to back it off all the way, but back it off substantially. Look how much I'm turning this. Turn and a half at least, okay? And bump this up here, hand tight. This is loose. And we thread this back on here until we just barely feel it touch. Now it's snug again. torch I operate at home. I have a demonstration machine. I mean, any student can use it. I don't have a problem with that. But since I use it all the time, I have a medium back cap, and I have a TIG torch on there, and I can use the same components for years and not replace them because I don't over tighten anything. Next thing is the cup. Standard collet body, standard cup. There is a number on here. These are whole numbers. 4, 5, 6, 7, 8, 10. The whole number indicates the ID, the opening here in 16ths. So a number 7 cup would be 7/16, 0.4375 for you decimal hounds. And I'm going to thread this up in here gently till it touches and seats into the insulator. Now we have a seal for our gas. As gas is forced into the cup, it's not coming out the backside because we mentioned the O-ring. We're threaded in here and we're snug. I got to back that off and answer your next question, which is, how far can I stick that tungsten out of that cup? Okay, as a general rule, if you have a number 7 cup on here, which we do, then you can stick it, they can extend the tungsten out about 7/16. You have a window. I know that we do a lot of videos and we'll stick it out there so that we can get a good camera angle for you to see. That's what we're going to do today. So to review, we've inserted a collet and collet body. We've inserted the back cap. We've slid the tungsten up here. We have things properly seated. I'm snug. I turn that back a quarter of a turn, I'm loose, okay? Turn that back, it bumped, I'm touching again. I guess at this point we could talk about the tungsten. Today I'm using a 3/32 E3 tungsten, and I have sharpened this to a 30-degree point. Just gonna keep it real simple. I just want that taper, that point on there. Yep, that's pretty sharp. So, we want to demonstrate how to hold the torch. I want to demonstrate some problems that we can run into with too long of an arc, too much angle. We just want to keep it simple and run some beads. Next thing we need to do is set up our machine. So we need gas, post flow. Post flow is for this. When I get through welding, this tungsten is red hot. It needs time. It needs to be protected from the atmosphere by an inert gas while the tungsten is cooling down. So I need to give it several seconds, otherwise it can become oxidized by the atmosphere. I've had a lot of students say, well, post-flow cools your tungsten off. Really? I'm pretty sure that gas is superheated as it's been running through a superheated tip here or torch. So think of post-flow as protecting your tungsten as it's cooling off. You can also use post-flow over material. Good habit to get into. When you terminate the arc, leave your post-flow over your material. Not critical on carbon steel. It is critical on stainless steel. It helps out a bunch. So, let's set our machine up and get to welding. We have our TIG torch put together, and now we need to get some gas behind it. Real simple. We're going to put a regulator flow meter onto this cylinder. And here's the important thing. There is a ball in here that floats for your flow, your adjustable flow. We need to always turn this on slowly. Okay, you come over here and it doesn't matter if this is cranked down all the way with no flow. You come over here and rip this cylinder open, it sends that ball up inside this tube. And I've seen them crack before, and then you got to send them in for repair, or you got to replace this inner tube. So always come over here and open this up slowly. See, the ball just jumped on its own there. And then we're reading tank pressure at about 1,200 something pounds, PSI, pounds per square inch. Okay, so if we just turn that on slow, then we're not going to destroy our flow meter, regardless of brand. Now we need to turn the machine on and go through some simple settings, and I will reach over, step over, and I will depress the foot pedal to make sure that we have the proper flow. And we only need about We're in a shop here with no wind blowing. We could get by with 15 cubic feet to hour. I'll probably set it at about 15 to 20. So let's turn the machine on. We'll step in here. On this particular machine, which is an Everlast Power TIG 200 DV, I want to set 125 amperage. 125 amps. We're on DC, direct current. I don't want any of the pulse or any of the other features on there. I am on 2T pedal. I'm going to be operating off of a foot pedal. It's going to have a high frequency start. The only other thing, I don't want any pre-flow. All I want is about 7 to 8 seconds of post-flow. We talked about post-flow and how we're protecting the tungsten as it cools off so that it doesn't oxidize to the atmosphere. Turning all this other stuff off, it's not even in the circuit, so real simple. DC, 125 amps, high frequency start on the pedal, 7 to 8 seconds of post flow. It's all I want to do. Okay, let's get down to the business end of this. How does all this work? What are we doing? Gas tungsten arc welding. We're using the tungsten as a heat source. That is the arc. We have inert gas, in this case argon, flowing through our nozzle to protect the weld pool from the atmosphere. So when we weld, this is always a forward process. It's always a forward process. With MIG welding and stick welding, there's a drag angle or a push angle. This is a push angle at all times. If you try to drag TIG, sometimes you'll get, it's like a Venturi effect. You get a air pocket that gets introduced in here and you create porosity. Porosity is bug holes in your weld. It's not fun. So this is always a forward angle. Now I have this lean forward. I want to say that's about 10 or 15 degrees or so. And I want to start here and I want to weld in this direction. If I was going to do this right-handed, I would do this just the opposite. And I would lean it this direction and weld. I would lean it back over here and do this in this direction, right to left, about 10, 15 degrees. Does it have to be exact? No. You do have a window. You can go straight in. You can lean this forward a little bit more. But here's what I've seen happen. I've had people come in and they want me to get them going, and I'll demonstrate it, and I'll demonstrate just running beads, which is what we're going to start out doing. No filler wire. We're just going to run some straight beads. And I'll demonstrate it. I'll step away and they'll go over to their booth and they'll come back and they'll say, what did I do wrong? And they'll have this hazy brown, we'll reproduce it, I'm sure. We'll have this hazy brown looking, weird oxide looking on the plate. Here's what's happened. They've leaned this torch way over like this. That's one of the things that can cause it. They'll lean this torch way over like this. Okay, and they'll try to weld like that. Or they get too long of an arc. Okay, too long of an arc. The weld pool is not, it's not really underneath the tungsten. It's all over the place. And you have more of a chance of getting oxides in because your gas shield, your weld pool is outside of your gas shield. So we might be way up here. Things are going everywhere, okay? These folks may have gotten confused between here and the filler wire being introduced low. So probably what happened was, if I was demonstrating this is dead 90 degrees, and I leaned it over and said 15 degrees, and we may have been to the point where we were running filler wire, and I said, always keep your filler wire low down here. This is about 15 degrees from horizontal. This is about 15 degrees from vertical. Now here's another thing that gets real sensitive. If you can't see, you're not going to be able to weld. We need to maintain a short arc length, and when I say short arc length, this tungsten is right on top of the plate. it's touching the plate. Our arc length needs to be up here for optimum control. Let's say that it needs to be 1/8 of an inch, and we need to keep it right in there about 1/8. Okay, so if you have a hard time seeing that, then you're going to have a hard time doing this welding process. And I've experienced that with a lot of people over the years. You know, if you can't get this good focal point right down in here and keep your arc length about 1/8, then you may have trouble. Obviously, if you touch the tungsten into your weld pool, you're done. You need to stop, and you need to resharpen and clean this point on your tungsten. That's very important. I've seen a lot of people, I still dip a tungsten. I do it all the time. It happens. But I've seen a lot of people, they'll dip and dab, and they'll get this tungsten all manked up on the end. It looks like a Q-tip, and they're trying to weld with it. Not good. We're going to reproduce all these problems that can go on. One more thing as far as vision. If you don't have clean lenses on your hood, if you are one of these that this thing is all dusty and it's had welding sparks and stuff all over it, and it's brown and cobbled up, and the inside is all scratched up, then you might as well just smear some mud on your windshield and go on a foggy day and go drive the interstate, because that's about the same thing, really. If you can't see out of your hood and you can't acquire clear vision, you're going to be in trouble with this process and with a lot of processes. You can't see the edge of the weld. The edges of the weld, the bead height, those are all critical things. So fresh lenses, take care of your equipment. It's vitally important, I think, for your success. So let's get some gloves on and we'll run some beads, and then we'll create some problems. We'll do some things wrong. Okay, we're ready to weld. Again, this is a forward process. I'm welding left-handed. I've got this set up where we can film it, we can zoom in close. The arc length needs to be about this distance away, about 1/8 of an inch away. I always need to keep the tungsten off of the material, but I don't really want to exceed this 1/8 of an inch. And we will show you what happens when you do, if you do. So just to run a couple of simple beads, I'm going to depress the foot pedal to initiate the arc by high frequency. This machine, I don't need to touch the tungsten to initiate the arc. So when I depress the foot pedal, the gas is going to come on, the amperage will come up, the arc's already initiated, the amperage will come up. I'm just going to slowly push it all the way down. I'm using 125 amps. Let's see what that looks like. I'm going to do that again. The width of my bead is approximately 3/16. I'm going to do that again. It also felt like I was pretty much straight up. I'm going to lean this toward me about that 15 degrees we were talking about, and just run a normal bead. When I terminated these two beads, I came over here and I just slowly, normally left off the foot pedal. It leaves a little bit of a button glass right here, the silicon deposit or the impurities from the material. Not that big a deal. They're clean. There is a couple of floaties in here. I'm not alarmed by it. One more time. That time I let off the foot pedal slower. You saw the arc taper out a little bit. okay? All these beads are about the same width. Here's why. My travel speed is fairly consistent. By the way, I've got my wrist up here, and I'm sure with this cranked up high power zoom lens that we've got, you can see every bit of my shaking going on, and that's kind of normal. Sometimes when I get my wrist up here, I get to really going at it. But I'm just trying to relax. I'm hanging on to this lightly. Your travel speed is your bead width to a certain extent. Okay, with this process, if I'm running along normal like I have been here, and my bead width is about 3/16, if all of a sudden I increase my travel speed and speed up, my bead will get real narrow. Okay, so let's do one of those. I'll run about half of this normal. The second half, I'm going to race forward and show you what your bead would look like if you increase travel speed. I'm blending these beads together. You may not be able to see that. Let me run that one more time and away from these beads. So when I started out, I started my normal speed, 125 amps. All of these beads are running at 125 amps. I'm not doing anything to the amperage. I'm not doing anything with the foot control. So this is pedal all the way down, 125. I started out at normal speed. When I got to about right in here, I increased the travel speed quite a bit. The width of my bead became narrow. Now, with this particular process, with gas tungsten arc welding or TIG welding, I'm going to do just the opposite. I'm going to start out and go normal speed to about right in here. It should look just like this, and then I'm going to slow way down. But I don't think it's going to matter a whole lot. I don't think the bead is going to get real wide or do anything drastic, not like this here. So let's experiment with that. So on this bead that we just ran, we started what we normally did on all these other beads. We started out and we ran our normal travel speed to about right here. And then we slowed way down and we ran along here. About all I'm doing, it got slightly bigger. What you really see is all my little movements in here. Everywhere there's a little ripple in here is me moving and jerking around. When I got out here to the end, I just stopped and paused and left it on 125 amps. The bead didn't grow real big. That's the only thing I did was just pour a whole bunch of heat into this is all. Okay? So, things to remember. If you want the normal travel speed, you're going to get about the same width, and that's what you want. If you race forward or you vary your travel speed between normal, fast, normal, you're going to see variations in width of your bead. So one of the exercises that we try to do with this process is to take a plate like this and try to run straight line beads all the way across the same width and just try to make them straight, same width, make them all exactly the same, as close as possible. It's a good exercise. Okay? Now, how about we do some problems? How about we create some things that we talked about with too long of an arc? I'll even stub one into the material We'll change the angle quite a bit. We'll change the angle and increase and see what happens. First thing we need to do here, we're going to create some problems. So the first thing we need to do is probably do too much torch angle. We've been saying that we need to go about 10-15 degrees in a leading angle and go this direction. So let's lean this rascal over and go way over here and just see what happens, okay? Not much. I am probably a little amazed that it stayed together and didn't get porosity. The bead is narrower. I know I'm not directing this arc down into the material, so let's try that again. One thing I did notice was the bead didn't have the normal arc shape to it. It kind of started out and laid in there at an angle. So let's try that again. I know I'm not directing this into the plate as well. The bead is automatically narrower. I'm doing normal travel speed, normal amperage. I did notice that I had this thing laid down so far that I'm dragging the cup in here. And as I'm dragging the cup, it's making it hard for me to move. So I wouldn't learn how to do welding that way with this process. I wouldn't learn how to TIG by leaning it way over like that and keeping it clean. I still like this control type thing where we're directing the arc into the material. Now let's do this. Let's start out normal arc length, and I'll start increasing the arc length where it's way too long. We should see variations in the width of the bead. We may see oxides. Let's give it a go. Wow, that's extreme. Again, we have porosity. We have created porosity. But I didn't get that brown, nasty haze look. This series of bug holes in here, this one over here, we do have a slight variation in width. But again, this gas envelope must have been reacting to the point where it kind of protected it. But we have created porosity. We do have a color differentiation here between, nice and clean. We got dark and weird down here. But that's what I've seen. I've seen people that, I guess they just see the bright light. They can't judge that critical distance because they can't see the tip of the tungsten, so they have no clue where that arc length is. And that's how they get that long arc on there. Now let's go through a couple of scenarios. I need to show you how to correctly add filler wire. I need to show you how to incorrectly add filler wire. I probably need to go ahead and stub the tungsten into the molten weld pool. That's always fun. That will get me up to out of the chair and over to the grind bench to redress the tungsten, okay? Correct way to add filler wire. I'm leaning the tungsten normal arc length. I want to introduce filler wire on the leading edge of the weld pool. What I don't want to do is melt the wire with the arc and have it fall onto the material. It's not cool. Correct way to add wire, in my opinion. Dab, 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 dab. Bead width was slightly narrower than our normal runs over here without filler wire. And you'll see ridges in here. Every one of those ridges is when I was adding filler wire. It cools the pool. It's a mass going into the molten weld pool, and that's what creates that ridge in there. That term everybody uses of stacking dimes, that's every time they add filler wire in there. How much do you add? I personally like to think, whatever, when I'm doing this process and this exercise, whatever the filler wire diameter is, that's how much I'm kind of pushing into the weld pool. Let me show you a different method where I'm just barely touching the pool, and I'll do it multiple times quickly. Again, this is still clean. This is yet another method. And I don't personally care for this method because I think it builds bad habits when we get into advanced joint configurations, but let me show it to you. Knowing how to do that is fine, but when we get into aluminum work or we get into some stainless work, we need to be able to be accurate and control that filler wire and put it on the leading edge and actually push a little bit in there, especially when we get to the aluminum part of it. Thin, low-crowned aluminum welds, in my opinion, are weak. We need to kind of push some material in there so it'll sink, and that's where you get that dime effect, that stacking effect. Okay, we need to run some more wrong here with the filler wire. When I said we don't want to melt the wire with the arc, we want to put it in the pool. Let's see what that looks like real quick. I'm going to run over some of these clean beads over here to begin with. Long arc and melting the wire with the arc. I've got two things going on. Okay, I got a couple of things going on here. I'm not in control of my weld pool per se. Yeah, I'm making one, but I'm also making turds and they're falling on the plate. Turds are coming off the end of the wire here. There's one of them. Nice little turd. Okay, so I'm forcing myself to weld bad here, and you can see the results. That's long arc, and I'm not directing the arc down into the plate to create the pool. I'm kind of long arcing, and I'm making the wire melt off with the arc, and then it's falling. Hopefully it falls in the right spot. Let's go for the old tungsten dip here. I should be real good at this exercise. I'm going to create a weld pool, weld for a little bit, accidentally stab my tungsten into the molten weld pool and see if I can keep going. Okay, I'm going to stop right there, and I'm also going to hold it right there for a reason. And I've seen this happen many times. Remember when I said everything is soft copper and brass alloys? Fine threads and stuff, plus your torch is heated up. If I go jerking around on this thing and trying to break this tungsten off, what do you think I'm actually doing? Yeah, I'm kind of tearing up that collet body thing. Cool thing to do, if you're cool, is remember, come up here and loosen this and extract the torch off of the tungsten. That's the cool thing to do. Also, while we're on that subject, tungsten is extremely brittle. So I'm going to try to recover this. And I reached down here and broke it off. So I no longer have the integrity of my sharpened point. So now I'm going to start welding without a clean sharpened point, and we'll see what happens. Well, this is pretty amazing. Here, I'm trying to mess everything up and it's welding just fine. You know, I really thought that was going to get all tore up, and I've got a crappy end on here and it welded kind of good. So now I want to stab the filler wire into the tungsten while I'm welding, see if I can do that. So now I actually put the filler wire onto the tungsten with a normal arc length and created a Q-tip. I've done this a lot, teaching myself how to do backfeeding on open root piping and stuff. Stop, let it cool off, break that end, and redress it completely. But we're gonna weld with it to see what happens. This is where I think that we might produce the weird brown, orangey looking haze, the nasty contamination stuff. So let's go over one of these beads over here and see if we can get it. All right, well, some of you know me well enough. Some of you have just coming on and seeing this for the first time, but I'm doing everything to kind of mess up, and it's actually doing better than what I thought it would. I have labored to produce a Q-tip on the end of this rascal here, and I thought when I'd start out, that's the last bead here, I didn't get that orange color. I didn't get that weird stuff that I thought I would. One thing that we didn't do was weld on mill scale. All of these plates are cleaned of mill scale. Mill scale is, you may get brand new material. It could have this pickling, but this light gray on here versus this shiny. You need to clean all this off before you weld. Welding over the top of mill scale will produce some discoloration of your beads, and it'll look pretty bad. Could cause some porosity as well. Maybe that's where some of that brown orangey stuff comes from. Been a while since I've been able to produce it. Some of this just looks gray and weird, but I wasn't able to get the nasty colors I'm talking about, and I apologize for that. So to close all this out, to dress this tungsten, snap that rascal off, take it over and regrind a tip on it and everything. To close all this out, we put a TIG torch together. We talked about angles, arc lengths, clear vision, being able to see, running straight lines. We ran beads with filler wire, too long of an arc length, too much angle. There's all these combinations. Just keep it real simple and follow the rules of 1/8 inch to start out with, 1/8 inch arc length, 10 to 15 degree lead angle in the direction that you're traveling. Get used to running multiple straight lines. Add your filler wire, bring it in low, 15-20 degrees. Put it on the leading edge of the pool. If you have any problems and we can help you, make sure you get a hold of us. Really appreciate you watching Weld.com. Thanks for supporting us. Check us out on Facebook and Instagram. Hit that subscribe button down there and hit all those buttons down there. Hit that bell thing so you can get notification when good stuff like this comes out. Thanks a lot. Killing me. Shooting film. We're on location making movies. Camera guy, you are killing me here today.
Still rolling.
Yeah. I want to know what you did with my filler wire. Are you serious about that?